Saltwater is the universe's only undeniable fingerprint of life. Taste sweat on your lip or the metallic bite of blood on your tongue. The salt you taste is not chance. It is a memory of the ancient ocean that shaped the first cells on Earth. When early organisms left the water, they took the sea inside them. Every cell, every nerve, every heartbeat still runs on the same ions that once powered life into existence. We are the ocean carried forward by evolution. Salt water is not just liquid, it is energy, it is memory, it is life's universal constant, the element that lets life endure, where pure water would freeze or disappear. The question is no longer whether water exists in the universe, but how many oceans are still alive and waiting to be found. If saltwater is life's rule here, the universe should echo it. And it does even where life should be impossible. Vesta, once thought to be a dead rock, shows gullies carved by liquid brine. Salt lowered the freezing point, trapped moisture, and let water flow in the vacuum of space. Saltwater is not an Earth invention. It is a cosmic mechanism, a battery the universe keeps reusing. So if the cosmos carries this signature today, one question remains. Where did this current begin? To answer that, we must turn back not to the stars, but to the first ocean. To understand how this universal pattern began, we must first shatter the image of the Earth we know today. 4 billion years ago, there were no blue tranquil seas, no white sandy beaches, and certainly no breathable air. If you stood on the shore of the Archean Earth, you would look out upon a nightmare. The sky was a bruised orange, choked with methane and carbon dioxide. The moon loomed massive and close, dragging violent tides across the planet's surface. And the ocean itself was not blue, but a deep metallic green, stained by dissolved iron and saturated with volcanic ash. This water was hot, acidic, and chemically aggressive. It was a chaotic brew of minerals leached from the planet's restless crust. But within this toxic soup, the most important ingredient was already dissolving salt. Sodium, potassium chloride, and magnesium ions were flooding into the water, turning the global ocean into a massive, conductive medium. In this violent prebiotic world, the ocean was not just a basin of water. It was a planet-sized vat of chemicals waiting for a catalyst. It was a battery waiting to be charged. For decades, scientists believed life began in a warm little pond, struck by lightning. But the evidence now points to a much darker, more energetic origin, the crushing depths of the sea, at places known as hydrothermal vents. Here, superheated water from the Earth's mantle blasted upward, carrying a rich cargo of minerals. But it wasn't just heat that mattered, it was electricity. Recent research into sites like the Lost City Field reveals a mechanism that operates like a natural alkaline battery. The ancient ocean was acidic, rich in free protons, while the fluids venting from the crust were alkaline. When these two distinct fluids met within the porous towers of rock, they created a desperate chemical imbalance, a proton gradient. Nature hates imbalance. The protons from the ocean fought to cross into the alkaline vents to neutralize the difference. This flow of charged particles across the rock's honeycomb structure created a natural voltage approximately 200 millivolts. This is the stunning realization of modern biology. The spark of life was not a metaphor. It was literal bioelectricity. Long before there was DNA to store code or proteins to build structures, there was this flow of ions. This process, known as chemiosmosis, acted as the first primitive engine. It drove the simple metabolic reactions that would eventually knit carbon atoms together into complex chains. The salt ions in the water, specifically sodium and potassium, became the gears of this engine, facilitating the transfer of energy that turned dead geology into living biology. But energy without a container is just an explosion. For life to truly begin, it needed to capture this lightning in a bottle. It needed a body. In the swirling chaos of these vents, fatty molecules began to spontaneously organize. Driven by the physics of water, these lipids curled in on themselves, forming microscopic bubbles known as protocells. This was the defining moment of existence, the separation of self from the environment. Salt played the role of the architect here. The specific concentration of ions in the seawater helped stabilize these fragile membranes, preventing them from dissolving back into the abyss. More importantly, these protocells trapped a tiny pocket of that conductive saltwater inside them. This was the first act of biological preservation. When these primitive cells eventually drifted away from the vents, they took their environment with them. They maintained that specific balance of sodium and potassium within their walls to keep their metabolic engines running. This is why your blood tastes like the sea. We are not just living on Earth. We are walking capsules of the ancient electric ocean that first sparked existence. But as life evolved to conquer the planet, the ocean itself took on a new role, not just as a creator, but as the great regulator of the world. Just as salt regulates the pressure in your veins, it regulates the climate of our entire world. We often think of the ocean as a chaotic, sloshing bathtub, but beneath the waves, there is a structure, a massive, silent river, known as the thermohaline circulation. This is the planet's heartbeat, and salt is the muscle that pumps it. In the frigid waters of the North Atlantic, as sea ice forms, it expels salt into the surrounding water. This brine becomes incredibly dense and heavy, sinking violently to the ocean floor. This sinking action is the pulse that drives the global conveyor belt, pulling warm surface water, the Gulf Stream, up from the tropics to keep Europe and North America from freezing over. But this heartbeat is skipping. As global temperatures rise, glaciers are melting, dumping billions of tons of fresh water into the Atlantic. Fresh water is light. It refuses to sink. By diluting the ocean's salinity, we are effectively thinning the planet's blood. If the salt concentration drops too low, the sinking stops. The pump fails. The Gulf Stream stalls. This would be a planetary cardiac arrest. While the equator burns, the coastlines of the North Atlantic would plunge into a paradoxical ice age. The weather systems we rely on for agriculture collapsing into chaos. But the story of salt is not just a warning. It is a blueprint. For 2 centuries, human civilization has been powered by fire, by burning dead carbon. Now we are finally learning to mimic the engine of the Earth itself. We are moving from combustion to flow. This shift is happening in the laboratories of the future energy grid. Engineers are turning away from volatile lithium and looking back to the ocean. Enter the saltwater battery. Unlike their explosive cousins, these sodium-ion systems use the same principle as the ancient ocean, the movement of ions between fluids. In a redox flow battery, energy is stored not in solid metal, but in tanks of saline solution. They are non-flammable, incredibly cheap, and can last for decades. We are even using this ionic technology to scrub the sky. New direct air capture systems, also known as DAC, use salt-rich solvents to trap carbon dioxide using the natural hunger of ions to lock away the very gases that are heating our world. We are finally aligning our technology with the physics of our planet. We are learning that the most powerful force is not the explosion, but the current. If we have learned to master the flow of ions here on Earth, the rest of the solar system seems at first glance to have forgotten it entirely. When we look out through our telescopes, we see a graveyard, from the cratered gray husk of Vesta to the rusted deserts of Mars and the frozen white shell of Europa. Our neighbors appear locked in a state of rigor mortis. They are dry, irradiated, and motionless. For decades, astronomers believed that if a world was too far from the sun, water would freeze into stone and life would be impossible. But this surface desolation is a lie. It is a cosmic mask. The concept of the Goldilocks zone, that narrow band where water can pool on the surface, is outdated. The universe has a second habitable zone, one that does not depend on sunlight, but on shielding. Faced with the vacuum of space water in our solar system did not vanish. It retreated. It went underground, pulling the potential for life down with it into the dark. The solar system is not dry, it is drenched. We just haven't been looking deep enough. The first crack in the dry universe theory appeared where we least expected it, in the asteroid belt. Ceres, a dwarf planet that should be a solid block of ice and rock, is behaving like a muddy world. NASA's Dawn mission spotted a lonely, towering mountain named Ahuna Mons. It looks like a volcano, but no lava has flowed here for billions of years. Instead, it is a cryovolcano. Driven by the heat of its own formation, Ceres is sweating. But it doesn't bleed magma, it bleeds brine. A thick, salty mud cryomagma erupted from the depths, freezing instantly upon hitting the vacuum. This suggests that Ceres is not a rock, but a mudball world holding pockets of ancient briny sludge deep within its crust that are still shifting today. Move closer to us, and the story gets darker. Mars is a radiation wasteland. Its surface is sterilized by ultraviolet light and stripped of its atmosphere. Yet radar signals from the Mars Express orbiter have penetrated the ice caps of the South Pole and bounced back with a bright, sharp reflection. There is something liquid down there buried a mile beneath the ice. How does water stay liquid at 70 degrees Celsius? The answer again is salt. The Martian water is saturated with perchlorate's toxic salts that act as a powerful antifreeze. This creates a biological paradox. The very thing that keeps the water fluid, the perchlorate is toxic to most Earth life. Yet on Earth we find bacteria that eat perchlorates. The Martian subsurface is a chemical knife edge, a toxic, briny reservoir that might be the last refuge of a dying biosphere. But these are just pockets. To find the true engines of the solar system, we must travel past the frost line to the moons of the gas giants. Here water is not hiding in reservoirs, it forms global oceans. Europa, the icy moon of Jupiter, is the crown jewel of this subsurface reality. Its crust is a shell of ice as hard as granite, 20 kilometers thick. But beneath that shell lies a saltwater ocean, 100 kilometers deep, containing twice as much water as all of Earth's oceans combined. It is pitch black down there. The pressure is crushing, but it is not dead. The gravity of Jupiter needs the moon's core generating heat that keeps the ocean liquid. We believe that on the seafloor of Europa, hydrothermal vents, just like the ones on ancient Earth, are roaring in the dark, spewing nutrients into the water. And then there is Enceladus, the tiny moon of Saturn. It doesn't just hide its ocean, it sprays it into space. Massive geysers erupt from the South Pole, shooting plumes of water vapor and ice hundreds of miles high. The Cassini spacecraft flew directly through these plumes and tasted them. The verdict: salt, along with organic molecules and silica grains that only form in hot water. Enceladus is offering us free samples of its deep sea, proving that the ingredients for life are cooking just beneath the crust. The most shocking revelation, however, comes from the largest moon in the solar system, Ganymede. Ganymede is bigger than the planet Mercury. For a long time, we thought it was just a cold, inactive world. But when we sent probes to measure it, we found something impossible. Ganymede has its own magnetic field. Planetary magnetic fields are usually generated by a spinning core of molten metal. But Ganymede's core shouldn't be active enough to create the signal we see. The best explanation is an induction mechanism. Jupiter's massive magnetic field sweeps over Ganymede, and something inside the moon is conducting that electricity, creating a secondary magnetic field that fights back. That conductor is a saltwater ocean. Models suggest Ganymede is a club sandwich of alternating layers of ice and water with a massive electrically conductive ocean trapped between high-pressure ice shells. It is a planetary-scale battery. Even at the frozen edge of the solar system, Pluto is breaking the rules. The New Horizons mission revealed a smooth, heart-shaped plain called Sputnik Planitia. The geology implies that the crust here is sliding over a viscous, slushy layer. Beneath the nitrogen ice, Pluto likely holds an ocean of ammonia-rich water insulated by a cage of gas hydrates. From the inner asteroids to the Kuiper Belt, the verdict is clear. The solar system is not a desert. It is an archipelago of hidden seas protected by armor of rock and ice. But if water is hiding here, could it be hiding everywhere? To answer that, we have to look beyond our own sun to worlds we cannot reach but only observe. We have drilled into the rock of Mars and tasted the plumes of Saturn's moons, but our physical reach ends at the edge of the solar system. To find water in the wider galaxy, we cannot use drills or rovers. We must use the only thing that can cross the abyss of spacelight. This is the era of the cosmic detective. When a planet passes in front of its star, starlight filters through its atmosphere. The gases in that atmosphere absorb specific colors of light, leaving behind a unique barcode, a spectral fingerprint. By reading this barcode, we can sniff the air of a world hundreds of light years away. For decades, we hunted for the simple signature of water vapor. But water alone is no longer enough. We are now hunting for the context of that water. We are looking for the chemical imbalance that only life can create. The investigation has already identified a prime suspect. 124 light-years from Earth in the constellation, Leo lies K2-18b. It is not a rocky Earth twin nor a gas giant. It is something new, a Haitian world. These worlds are massive, covered in global oceans, and wrapped in a crushing atmosphere of hydrogen. The pressure would be lethal to us, but the water beneath might be warm enough to harbor life. When the James Webb Space Telescope turned its golden mirrors toward K2-18b, it confirmed the signature of methane and carbon dioxide, the chemical backbone of an ocean world. But buried in the noise was a faint and controversial signal, known as dimethyl sulfide, or DMS. On Earth, DMS is not produced by geology. It is produced by only one thing: life, specifically marine phytoplankton. If confirmed, this would be the smoking gun of extraterrestrial biology. But in forensic science, a single clue is not a verdict. The signal is weak, and the hydrogen atmosphere complicates the chemistry. K2-18b remains a person of interest, but the jury is still out. While K2-18b is shrouded in thick gas, another candidate offers a clearer view. Enter LHS 1140b. Located 48 light-years away, the super-Earth orbits a red dwarf star. Because it is so close to its sun, it is tidally locked. One side faces the star in eternal daylight. The other is frozen in eternal night. For years, we thought such worlds would be uninhabitable deserts, but new models suggest a stunning possibility. At the point directly facing the star, the substellar point, the heat is just intense enough to melt the ice but not boil it away. This creates a permanent circular ocean surrounded by a shell of white ice. It is an eyeball planet. Imagine a world that looks like a giant blue iris staring unblinkingly at a red sun. This pupil of water would be deep, stable, and circulating nutrients between the light and dark sides. Unlike the crushing depths of the Haitian worlds, the eyeball ocean might have a surface pressure we could actually survive. It is currently our best shot at finding liquid water sitting open to the stars. But the hunt is not without its tragedies. The TRAPPIST-1 system, with its 7 Earth-sized planets, was once our greatest hope. But recent autopsies by the James Webb Telescope on the innermost planets TRAPPIST-1b and 1c revealed a grim reality. They are bare rocks. The violent flares of their red dwarf star have stripped away their atmospheres entirely. They are not Earths. They are scorched Mercuries. This draws a terrifying cosmic shoreline in the galaxy. To keep its water, a planet must not only be in the habitable zone, it must be strong enough to hold its atmosphere against the solar wind. The hope for TRAPPIST-1 now retreats to the outer planets E and F. If they have managed to hold onto their water under the ice, they might be sanctuaries. If not, the system is a tomb. The difference between a dead rock and a living world often comes down to the resilience of its water. The search for life in the universe often feels like a hunt for a needle in an infinite haystack. We look for radio signals, for megastructures, for ships sailing between the stars. But perhaps we have been overthinking the answer. The universe has already given us the key. It is the same key that turns the lock of our own biology. We began this journey by tasting the salt in our own veins. We discovered that this was not a coincidence, but a heritage. The fluid that drives your heartbeat, that fires the neurons allowing you to read these words, is the same fluid that sparked the first metabolic engine in the Hadean Deep. Saltwater is not just a medium, it is a mechanism. It is the universal constant. Across the billions of miles we have traveled today, from the acid baths of early Earth to the mud volcanoes of Ceres, from the dark pressurized oceans of Ganymede to the unblinking blue iris of LHS 1140b1, truth remains absolute. Entropy wants to freeze the universe. It wants to strip away atmospheres, lock water into ice, and grind geological activity to a halt. But saltwater fights back. It acts as the cosmic antifreeze, keeping oceans liquid in the freezing dark. It acts as the planetary shield, generating magnetic fields that deflect the solar wind. It acts as the chemical battery, storing the energy needed to assemble the first chains of life. Wherever we find the resilience to survive against the cold indifference of the cosmos, we find salt. This changes how we look at the night sky. When you look up at Jupiter, do not just see a gas giant. See the shield guarding the ocean worlds of Europa and Ganymede. When you look at the red dot of Mars, do not see a dead desert. See a planet holding its breath, clutching a reservoir of liquid hope beneath its southern ice. And when you look at the stars, know that around them on worlds like K2-18b, the universe might be breathing back at us, its chemical signature written in the faint light of a distant dawn. We are not separate from this vast, cold architecture. We are made of it. We are the cosmic bloodstream that has achieved consciousness. We are the ocean that learned to walk, to build telescopes, and to look back at the stars to find its kin. The universe is not silent. It is just waiting for us to trace the flow. So the next time you look at the ocean or taste the sweat on your lip, remember, you are holding the blueprint of alien life. We just have to follow the water.